Welcome to the course. Today I want to talk about two things. First, data abstractions, and second, I want to start talking about multi-agent programming. Both of those two things. First, a few seconds of respect for the Ukrainians who are fighting for their freedom and for our freedom. Okay, so we saw last week the limits of declarative programming, so we're going to go beyond declarative programming today. And in order to start going beyond, I want to talk about data abstraction. This is partly a refresher, but I will also go deeper into certain aspects of data abstraction that we didn't see before. Data abstraction is the main... Oh, I'm really sorry about that black thing. I hope it doesn't bother too much. So data abstraction is very important. It's what makes large computing systems possible. And it's a piece of the program here. These two boxes together are one data abstraction. So it doesn't have to be the same part of the program. And there's logically one data abstraction. This is the inside. And then there is an interface. Here's a way of accessing it from the outside. And you have to follow a certain set of rules to access the inside. If you don't, then the data abstraction will not accept the operation. So the rules are enforced. And if you do that, then you guarantee that the data abstraction is correct. So this is encapsulated, and the programming language must guarantee that there is no way you can go inside and cheat, okay? The encapsulation has to be supported for this to be real data abstraction, okay? And let's talk about different kinds of data abstraction. I will use this simple example, which is a simple stack which uses a list. So nil is an empty stack. Push and pop will put an element on front of the list and take the top element from the list, and is empty will check if the list is nil. The stack is represented by a list. This is the implementation. This is not encapsulated, okay? These lists are not protected. That means the user of this abstraction can see the lists out without actually using the interface, which is these four operations. You can read the stack values. You can actually create your own stack values. They're lists. This is not protected. So this is not an abstraction, not a correct abstraction. It's an incomplete abstraction because it's not protected. The problem is we have to protect this, okay? And there's two main ways of arranging that, and these are called objects and abstract data types. They're fundamentally different ways of organizing data abstraction. And already in your programs you have used both of them, although maybe you don't realize when you're using each one. An object will group the value, so the internal state of the data abstraction, and the operations in a single entity, whereas an abstract data type keeps them separate. Okay? So for example, a television set is an object because it is a single entity and it has an interface, on-off channel selection, etc. So this is an example of an object. Whereas a vending machine is an abstract data type. You put coins in there and you get products out. A can of soda, for example, and the operation is the actual machine itself. The values are the coins and the products, and the operation is the machine, okay? So the idea is that the coin is already part of the data abstraction, and so is the can of soda, okay? And the machine. All of that is part of the abstraction. This is the real world, so we'll look at it in a computer, in a computing system, how it works. So the first one I want to explain is abstract data type, and this time I want to go into how you can fix it so that it's protected, okay? So in the previous course last year, I showed you this magic kind of encryption wrapping routine, but today I want to show you how it works. An abstract data type, so it's the set of values and a set of operations. Integers, 1, 2, 3, operations, arithmetic. And languages like Java have integers as abstract data types. They also have integers as objects, so it's kind of a language that doesn't really know how to do integers, because it has the both cases. But of course, so many languages, you are used to this. But it doesn't have to be numbers, it can be also very complicated things, okay? And the point is that most of the time, these values are constants. They don't have to be constants. I'll show you a case where it's not a constant. In fact, the vending machine example, the can of soda is not a constant because when you drink the soda, it's empty, so there's a state, but the coin is a constant. And in a programming language, most of the time, these values will be constants, and the operations also will be constant operations, no internal memory. And the only thing that's really changing is which operations, which values you give to the operations. And that's what I'll show you now, but I'll show you a little bit later. You can also have them have memory, have state. And that gives another kind of abstract data type. Okay? So let's implement our stack as an abstract data type. The values will be all possible stacks. So they're not just numbers, but it can be any stack value. And we have the 4 operations. New stack, push pop is empty. And we have these operations. We create a new stack. We push X on the stack S, and we get stack S2. So these stacks, S and S2, are values. Same for pop. We pop the top element, so X will be bound to the top element, and we have the new stack without the element, S2. Okay? And I'll show you an example later, but if you take a new stack, and then I push A, and I push B, then the stack will have B and A on it, so B is on the top. And if I pop S, then the new stack will be just A, and the top will be B. Okay, so you see how it works, huh? So this is what we saw before, the implementation. This is not an abstract data type because it's not protected. Okay? Because you cannot guarantee the good operation, that you're only going through the interface. That's essential, because programmers will, if they have the opportunity, they will look at the implementation. So the programming language must protect it. Otherwise, even by accident, they will look at it. They will say, hey, I can look at it. Let's look at it and do something. And for big abstractions, let's say you have a 10,000 line piece of code, which is an abstraction, that kind of cheating is very common. So the language has to make it impossible. Okay? So here, this is not protected. And the question is, how can we protect it and make it a true abstract data type? We want to define a new one. So in a language like Java, the integers 1, 2, 3, they are true abstract data type because you cannot look inside them, but that they're built in by the language. Now we want to define a new abstract data type and protect it. Okay? And the way we do it, so we have to protect the values. And only the operations can look inside. And the way to do that is we'll do a kind of encryption. It's called a secure wrapper. We will have a function, a wrapping function, which protects the value X, and an unwrapping which looks at the value, is able to look at the value. So these two functions are like a pair, and they have some kind of internal key that they know. So if I have the value x, I call wrap x, it returns w, and I cannot look inside w, it's protected. But if I call unwrap on w, then I get x again. So these are just functions, okay? And the idea is that only the implementation of the abstraction knows the functions, okay? And the way to imagine this is that wrap and unwrap are doing encryption and decryption, and there's a shared key that is only known by these two functions. So internally, they have a key, and they're the only ones that know it, okay? So for each abstract data type, we need a new pair of functions. If we define one abstract data type, wrap, unwrap, then if we define another one, it has to have different wrap, unwrap. Otherwise, there's like a leaking between the two. So each abstract data type needs a new wrap, unwrap pair. So we have a function called new wrapper. So this is higher order, which creates a pair wrap, unwrap. So when I call new wrapper, I will create a new one. So basically it generates a new key, a new shared key, and it returns these two functions. So this is a typical kind of higher order operation. I need to have a new encryption and decryption. Okay? And we're going to see how to implement this. Okay. So the point is that we have to build a secure encapsulation. There are languages that do not support it, older languages, like C or C++ or JavaScript. They are completely leaky. In a language like C or C++, you can do casting and you can actually look at what's in memory, at the bit representation. So that's completely very bad. In terms of software engineering, that's it's completely broken. So a language like Java, you cannot do that, okay? You have to have these unbreakable boundaries. And so for the abstract data types, we will use unforgeable keys. So the shared key has to be something that you cannot guess and you cannot forge, like for encryption. So the language has to support that. If you want to implement the wrapper in the language, you need to have the right concept, okay? And usually the language will not let you implement wrap, unwrap. It will provide unwrap, unwrap as magic functions, okay? But in this course, I want to show you how to implement wrap, unwrap. A language that lets you define abstract data types. Usually it has some magic boundary, magic thing that lets you protect the data. So you don't really know what's going on. But here I want to show you how you can actually program the wrap, unwrap, okay? And this is moving towards encryption, okay? So the way to do it is we need to add two things to the language. So it's like a new paradigm. Remember, you have the kernel language and you can add concepts. You add threads, or you add ports, or you add cells, you add threads for concurrency. Here, you need to add two concepts to the language because you cannot just do it without that. One of them is the unforgeable constants. These are the keys. Okay? So there's a function called names. So in Oz they're called names. And you have a function new name that creates an unforgeable key. So it's like a constant. N is a constant and it cannot be forged. That means you cannot even print it. It does not have a representation as a string or anything. You cannot print it. You can only pass it to somebody. That means it cannot be guessed. A program cannot try out strings, for example. Name is not a string, okay? It's not an integer. It's a new kind of constant that is not creatable except by new name. And each time you call new name, you get a new one, okay? So it's unforgeable. The only way that a program can know the name is if some other program gives it the name. There's no way to guess it. So this totally guarantees that it's unforgeable. Huh? You cannot guess it. Yeah?
Just to keep clear, because you mentioned encryption, this is different from encryption.
This is, yeah, so this is a language property. This does not need encryption to be implemented. It's a pure language semantics. But if you want to, if you have an adversary who can actually look at binaries, then probably you do want to look at encryption. But if the adversary is just a programmer who sees the source code, then that person cannot guess. So you don't need encryption to implement this. This is called language security. It's like also, it's for example, lexical scoping. The identifier in the scope, you cannot access it outside of the scope. So that's a language property. Here, the same thing. This unforgeable, the fact that it's unforgeable is defined by the language semantics, and it does not actually need encryption to be implemented if your adversary is only a programmer looking at source code, okay? Now, if your adversary is a person who can actually look at binaries or look at the memory, then you would need encryption, okay? But that's orthogonal. I'm going to talk today only about the language aspect, okay? If you want to protect the actual binaries, so usually programmers will not cheat so far. If I have a team of programmers building an abstraction and they use somebody else's library, usually they're not going to start looking at the binary because there's no need. They're going to use the abstraction from the other team. The other team would get very angry if they would, why are you looking at our binary? We are not guaranteeing anything in the binary. That can change all the time. You're an idiot if you do that, okay? But an adversary outside of the company might be doing that. Huh? But if you're building a large system with different teams, and each team has an abstraction that they want to protect, then you can protect it from the language point of view here. Huh? So this is a pure language semantics issue. And encryption is an orthogonal thing that you can add, but that you don't have to add. Okay? So I'm going to talk only about the language aspect of the security here. Okay? And it doesn't require encryption in the implementation to be protected at the language level. So you have two concepts. You have the unforgeable constants, which are called names in Oz, but they're just constants that you cannot even print them. You can't. They don't have any string or any printable representation. That means they cannot be guessed. And you guarantee that. In older languages like Lisp, there's a function called gensim, which generates a symbol, but that symbol is actually a string, so you could guess it. But it's not intended to be unforgeable. But here, it's not a string, okay? It's actual constant that cannot even be printed, okay? And the second concept is how do you use that constant? And this is, it's like a key in a lock. If I have a key that cannot be forged, I have to have a lock. And the lock is actually a record, a secure record, that only has the dot operation to access the field. It has no other operations. In Oz, normally the records have an arity operation that lets you see what all the fields are. But if the field is a name, okay, if the record field is actually a name, so an unforgeable constant, then the only way to access the field is if you know the name. So if I do n is new name, and then I have a record, and I have the field name is n, okay, the only way, this is r, if I want to access x, I can do r dot n, okay? So in order to access this protected value x, I need to know the name. This is the lock aspect. But normal records are not secure, because a normal record, you can do arity of r, and that gives you the list of field names. So that tells you what n is. That's not very good. That's completely unsecured. So the idea is that you have a version of the record type which only has the dot operation, field selection. It has no other operations, so it's a kind of restricted record, which I would call a secure record, okay? Now in Oz, they call this, in Oz this is called a chunk, okay? So I take any record and I can convert it to a secure record. So chunk.new takes a record and returns a secure record C. And C, I can do C.n. If I do C.n, then I access X, but I cannot do arity. So this is completely protected. If I only know C, I have no way of accessing the internals, okay? So with this I can build my wrapper. So you see I need these two operations, unforgeable constants, which are like keys, and a way of encapsulating something with a key, the secure records, which you can consider to be kind of like locks, okay? And with this we can actually build an abstract data type in the language. So now there's no magic, okay? I show you exactly how it's done. So here is how you can define new wrapper. So new wrapper is a procedure. It returns these two functions, wrap and unwrap. So how does it work? First of all, internally it creates a new key, a new name. And this one, the lexical scoping guarantees that key is only visible from between proc and end, so nobody else can know the key. But wrap and unwrap, they both know the key, okay? And what wrap does is it essentially just creates a secure record, and here I have a simple record, key : x. I put W as the label, doesn't really matter. So X is locked inside the secure record. And then the unwrap takes a secure record, W, and it just does W dot key. And notice that both wrap and unwrap they know key. It's part of their contextual environment. So they both have this shared key, but nobody else knows it. Only they know it. Okay, see how it works, huh? Wrap and unwrap. And now we can actually build an abstract data type, okay? There's actually a small detail. If key is wrong, if you use it in the wrong way, you have to raise an exception. So we actually put this in a try-catch so that we have a well-defined exception if there's a wrong argument, okay? But that's a detail for software engineering. Okay, and now that we have this, we can actually build a true abstract data type. And here is how it works. So notice I have a local end here, and I have these two identifiers, wrap and unwrap. So lexical scoping guarantees that I can only see wrap and unwrap in between the local and the end. Nobody else in the program can see it, okay? And so here I call new wrapper, so I create the new shared key and wrap unwrap to lock and unlock. And now I can build my abstract data type. So I have to protect things. So new stack, instead of returning nil, it returns wrap of nil, okay? And the push operation takes a wrapped stack. So how does it do that? Well, first it has to unwrap it to look at the actual stack value, unwrap W, then it puts X in front, X bar, unwrap, and then it wraps again. So essentially when you come into the operation, you start by unwrapping, then you do the operation, and before you go out, you have to wrap it again. So at the boundary, you have wrap, unwrap, okay? So let me see if I can make a picture. Just a sec. The board, let me write it here now. Let me make a picture of this. So the push operation, WX, it does wrap of X bar, unwrap W. I like to make pictures of it, so if you have it like this, the W comes in, you start by unwrapping, and then you add the X in front. This is the bar operation, and before you go out, you wrap. So you can see at the boundary, when you go in, you have to unwrap, and before you go out, you have to wrap. And here you have the actual operation inside, which is using the representation. This one is using the list, but the list is invisible on the outside, okay? Okay, so let me show you some code running here. This should normally create, this is the system. So here is the new wrapper. Paste. So this is how it works. But let me first show you how names work. So I'll create a new name here. Now if I browse the name, the browser respects the semantics, so it knows that it's a name, but there's nothing else that it can say. It's N. N is a name, and the identifier is N. And I can't print it. If I try to print it, it doesn't work. The print will not accept this. This has no print representation. Okay? And if I now create, let me create a wrap unwrap pair. Wrap unwrap. This is the, let me do it like this. Oh no, I have to compile this one first, of course. Sorry about that. Okay. Now I define this.
I say x is 100, and I do browse x, it shows 100. But if I wrap it now, wrap of x, and I do browse w, then it says it's a chunk. So it doesn't know what's, so the browser does not know what's inside. Nobody knows what's inside there. The only way to know what's inside is to use unwrap. So if I do the browse unwrap, then again I can see 100. So this W is a completely opaque thing. You cannot look inside it, okay? Okay, so you see how it works, huh? Okay, so that tells you how stack abstract data types, or any abstract data type, can work using the keys, okay? Okay, so that's all I want to say now on abstract data types. They're very old, okay? It's actually just as old as object-oriented programming. There was actually languages developed specifically for it. The most famous one, the first one is called Clue, which was developed by Barbara Liskov, who did a lot of other things, and later she got the Turing Award, which is the Nobel Prize for computer science. So this was 1974, and this is almost the same time as the first object-oriented language, Simula 67 in 1967. These two languages were like pillars. They influenced many languages up to today. C++, Java, Smalltalk. Every language today was influenced by this. So the language Clue has a similar wrap concept like wrap on wrap, but it's magic. Inside Clue you don't see it. You have syntactic support. You can create abstract data types, and there's a behind the scene, there's a wrap on wrap, okay? And other languages also support abstract data types. So Java actually supports abstract data types. So it's not so well known, but Java objects are actually also abstract data types. They're not pure objects. So a pure object would be something where you cannot look inside. But Java objects are actually abstract data types. But I won't get into that now. But in fact, languages today, they support both things, okay? So when people talk about object-oriented programming, they're kind of being too narrow, because most object-oriented languages also support abstract data types, okay? The name is not so sexy, maybe, I don't know. Object is like, woo, okay? But languages also support abstract data types. Okay, so that's all I want to say about abstract data types. Now let me talk about objects. So this is going to be kind of a refresher, but I'm going to give you also the semantics of an object. No hand waving. What I'm going to show you, you can see it as the actual semantic definition of an object. Okay? So in an object, it's not like an abstract data type where you have stacks and operations. The operations and the value are kind of melded together. And here's our stack object. So I create a stack object S, and then S itself knows how to do the operations. Okay? So this is called a message sent push X. You can send it to S. So the object itself also knows the operations, which is not true for abstract data types, huh? The stack, you have a set of operations and you have the stack value and you give it as an argument. Whereas in an object-oriented language, the operations are part of the stack. Okay? So this is something you know, so I'm not going to go so much in detail. I will give you the two main definitions. This is a typical definition of a stack object. This is a semantic definition. In the languages, usually they have a syntactic support for this, which is called a class. But here, everything is shown. This is kind of kernel language. So this is actually the semantics. You can see this as the semantics. And what I do is I create a new stack. And a stack is actually a one-argument procedure. So here, this is an anonymous procedure with a dollar with one argument m. And depending on the value of m, push x, pop x, or isempty it will call one of these procedures. These three procedures are usually called methods, and they usually have some syntactic support, and they have an internal state. So the object usually has a cell inside, or more than one, which is called the attributes. Okay, here is a stack with one attribute, which is the value of the stack. If I do a push x, then c will be assigned to x bar the old value. Okay? If I do pop x, first s is the value of the stack, c will be assigned s dot 2, so I'm popping off the top, and x will be equal to s dot 1, which is the top. Okay? So these three procedures are the methods. So usually there's syntactic support. But here there's no syntactic support. I'm showing you the pure definition in terms of kernel language, okay? And since we know what procedures and cells and records are, this is actually, you can see it as the semantics. So nothing is hidden. If I show you a Java object class, you don't actually know the semantics, you just know the syntax. But here, this is the actual semantic definition, okay? And the way you access the methods is using a procedure with a case statement. This is called procedure dispatching. So there's actually two kinds of ways of doing this. Procedure dispatching and record dispatching. So the object, semantically, it's a one-argument procedure, okay? And you have a method, which is actually a message, which is actually a record. And this record, there's a case statement that will select the method, okay? Dynamically at runtime. Of course, the compiler can optimize and so on, but technically, this is dynamically selected, and in languages like Smalltalk, it's completely dynamic. That means you can actually create a new message on the fly and send it to the object, even though the compiler doesn't know, and it will select the right method, okay? And this cell here, you can see it's hidden inside using the static scoping. Notice you do not need wrap and unwrap here because of the static scoping, because we're using state. So the state is hidden inside, and you can update the thing, okay? Because an object, because it's combining the operations and the data, it does not need wrap-unwrap. The wrap-unwrap, you need it because the values can live outside of the operations, and they have to be protected when they're outside. But here, everything is always inside, the operations and the value, so you don't need to wrap-unwrap, okay? So this is one way of defining object. The other way is called record dispatching. Instead of a procedure, a one-argument procedure with a case, I create a record here, and the dispatching is done using the records, the dot operation, okay? So some dynamic object-oriented languages, they would do either one or the other, okay? So this is called record dispatching. You can actually do stack dot push or dot pop to get the right method, but otherwise it's exactly the same. And in this slide, I'm actually comparing this with the abstract data type. So you can actually directly compare them. You don't need wrap-unwrap here because the values are always inside. They don't have to survive outside, whereas here they do, okay? I create a new stack, nil is the value, but it's outside, so you have to protect it. And then you do a push, and then you have to unwrap it. But here, when you do the push, both the cell and the push are both inside the implementation, so you don't need the wrap, because the value does not have to survive outside. Okay? So it's kind of interesting. Any data abstraction can be implemented either as an abstract data type or as an object. So there's nothing, any data abstraction you can decide, I want it like this or I want it like this. Okay? Because either the things are together, the values and the methods, or they're separate. Okay? You can decide. Okay, so a few comments on object. So objects, of course, are a big thing, but it comes, like I said, from Simula 67. And then there was a language called Smalltalk, which is still used, which was in the 1970s, and C++, which was the end of the 70s, and then lots of object-oriented languages. So most usual kind of mainstream languages will be object-oriented languages, but that's kind of a wrong name because they also support abstract data types, all these languages. So a better name would be data abstraction languages. They are languages that support data abstraction. So that's a very important thing, of course. And when this happened, which was around the real transition when Java and so on was done, happened in the 1980s, and object-oriented programming was a big thing. And I remember before that, in the 1970s or 60s, people did not use object-oriented programming at all. People did what they call structured programming, where you have, the big problem was you had languages with goto, and you want to get rid of the goto or replace it by things like while loops and if statements. So that was the big thing in the 60s. And then the 70s went beyond that and started supporting real data abstractions. Okay? So both objects and abstract data types. Okay? Okay, so that's objects and abstract data types, but it's actually more. There's actually 4 kinds of data abstraction, and this is something that many people don't really understand, even in industry, even today. So I'm going to show you all 4. I showed you already these 2 abstract data types, where the values are constants, and that means they're purely declarative. They don't use cells. So the stack I showed you is not using cells at all. So it's actually purely declarative, okay? And the object I showed you is using cells. So it's not declarative. Remember, we have this barrier. So, but that's actually kind of strange. Why are abstract data types purely declarative, and objects, they have attributes that you can change? So why is that? It's purely historical, actually, because that's how the first object-oriented languages were made. They started from imperative, non-declarative languages like C, and they added objects. But this is not absolute. There's actually 2 different other kinds of data abstraction. You can actually have non-declarative abstract data types, and you can have purely declarative objects. This is something that people don't really understand, so this is something that it's important for you, because these things are, in the past, they were not so much used, but they're starting in some languages to be used a little bit, especially the functional objects are coming up, okay? So that actually makes 4 kinds. And let me show you how these 2 work. I'm going to show you again how these 2 work. So I showed you how to implement these 2, but let me show you how to implement those other 2, okay? So we can make it first a diagram here. So we have 4 kinds of data abstraction. One axis is whether they have state. Do they have cells inside, or are they purely declarative, which I call stateless? And the other side is whether the values and the operations are separate. So this is what I call unbundled, or they're together, which I call bundled. So add ADT or object. And this gives you 4 things. So a Java integer, for example, would be an abstract data type with no state, whereas a typical Java object would be an object with state. But now you actually can see languages with functional objects. This is actually used in big data. It's kind of funny. People are starting to like these things. And there's a language called Scala, which is a kind of extension of Java. And there's things called fluents in some of the big data tools that are actually functional objects. But the 4th one is not really used so much, okay? Maybe someday it'll be used, okay? So this 3rd one is kind of coming up. And these two are like the traditional ones that exist for a long time. So this is kind of new thing. And this 4th one is still kind of not so much used, okay? So you have these two other ones then, a functional object. So this is like an object, so it combines the value and the operation, but it doesn't use cells. And if you have not seen how to do that, it's actually kind of very weird. It's a very interesting use of higher order programming to define this. So you cannot change the attributes. So how does it work? Well, you invoke an object, it actually returns another object with a new value. So you cannot change things. Now you don't have cells, but you can create new objects. So you're creating new objects all the time here. And the second one is a stateful abstract data type. This actually was used before in C, the old language C. You built something which looks like an object, like a struct, a record, and you put stuff and you update the values. So the values can be updated, okay? And you can see it a little bit. If you have a class with a static attribute in Java, so a class is a value, okay? And when you send that class to the new operation, it creates an object. So the class itself is an abstract data type. And if it has a static attribute, that means you can update the actual class value by updating the static attribute, if you understand Java. So you can see that it exists. Okay, this is an example of a stateful abstract data type, okay? But it's not so much used. Okay, let me show you the functional object. Now this is an amazing use of higher order programming. So I really recommend that you run this and try to use it. Now, how does it work? I have a function called stack object. And the argument is the value of the stack. And it returns, whenever I do one of these operations, the push and pop, it returns a new object. Okay, so stack object, if I call it, will create, this is record, so the record is an object. But when I call push, I can't update anything. So what do? I return a new stack object. So it calls stack object recursively with the new state. Okay? So that means that stack object is part of the contextual environment of push. So this is actually a really interesting use of higher order programming. Okay? And it's semantically very interesting because there's no cells here and no secure wrappers. This is actually the simplest of all data abstractions because it only uses static scope and higher order programming. It does not need cells, it does not need wrappers, so it's actually very, very simple, okay? It's the simplest form of data abstraction that you can get. But most of the time, people don't use this, and if you have not used it, it can seem kind of weird, okay? But it is a true abstraction. So this is actually the simplest form of abstraction, okay? So I have to show you how it runs. Okay. Okay. Let's see if I can again create. Here we go, the Mozart system. But let me show you now. So this is a functional object. Here I have it with a little bit better indentation, so maybe this is a more readable version. Okay. So stack object. This only does push and pop, simple version. Push X and pop X is bound to the top. And so it's a record with push and pop. And the new stack is just a stack object whose value is nil. So the state of the object is actually the argument of stack object. Okay? Okay, so I compile that. So let me show you how this works. So S is a stack object now, and one with a value nil inside. What does it look like? Here it is. So this is a record. This is using record dispatch. So it has two operations, push and pop, but I don't see the value. You see the actual value, this is a stack with nil, huh? It's hidden inside there. But if I want to do an operation, I do something like this, S2 is equal to push, S dot push, and I put A there. You see, it's actually very functional. Huh? I take S dot push, so it's using the push method here, and A is going to be the thing I put on the stack, and it returns a new stack. So S is not changed. Huh? So what happens when I browse S2? Well, it looks exactly the same. So S2 is a stack with one value there. See how it works? S is not changed. It's pure functional here. It's kind of very interesting. So play around with it. So this is something I really want you to understand, the functional object. Okay? It's a really neat use of higher order programming. And languages use it, okay? It's not unused. This is actually used. Of course, they're not going to show you the definition like this. But basically, you have something, you do an operation, you have it's like a bunch of data, and you do an operation on the data, it's like a pipeline. And you get a new bunch of data. Well, the old bunch of data is not changed. So that's exactly a functional object, okay? In big data, the S could be like a big bunch of data in a big data system, and you're doing a transformation on the data, and it returns the new version of the data, but the old version is not changed. Okay, so that's a functional object. Okay, so Scala is a language that supports this. Scala is a very interesting language if you haven't used it. Actually, a colleague, Pierre Schoss, is using a lot Scala for his research. Scala is a language that's both functional and object-oriented. And the interesting thing is that it uses the same virtual machine as Java. So it's completely interoperable, combinable with Java. So it's like a future next generation kind of Java. And in Scala, we can define an immutable object that returns another immutable object. That's exactly, an immutable object, exactly a functional object. Huh? You can define a rational number class whose instances are rational numbers, and so they're immutable, like 3/4 or 5/6. And if you add two rational numbers, it returns another rational number. So that's funny because it's like it's like you're defining really new kind of data type that are immutable, but they're still objects, okay? Okay, so let me finish this data abstraction discussion by showing you kind of the most complicated one, which is the stateful abstract data type. And this is like the opposite of the functional object. So the functional object was very simple. This one is using both wrapper and cells, okay? So, it's kind of a, so you have wrapped things, but what you're wrapping is a cell, okay? So the new stack is a wrapped cell, the empty stack, and the content of the cell is nil. And when you update it, you actually, inside the wrapper, you update the cell. So you don't have to wrap again. So if I do push, I will look inside. So C is what's inside, so that's a cell. I will update C, but it stays inside the wrapper. It's kind of like I have this secure thing, and I put my hands inside, and I'm modifying what's inside, but the secure boundary is still there. It's a funny kind of way of doing things. So when I'm doing push, I have to do unwrap, but I don't have to do a wrap. The unwrap tells me what's inside, but there's a cell inside, so I can just update it. Okay? So only the new has to use a wrap. All the operations that do something will only do unwrap. Okay? They don't have to do wrap at all. So this is another funny kind of data abstraction using both a cell and a secure wrapper. Okay? So this one is not so much used, but it could be, maybe it will. It's still a data abstraction, okay? Everything is protected, but it's a funny data abstraction. But the vending machine is kind of like this. If I put a coin in a vending machine, and the coin is a value, it's a constant, and the vending machine returns a can of soda, but that can of soda is like a wrapped cell, because I can drink the soda and then it's used up, okay? And so it's like I'm modifying the value, okay? So this could still have some use, okay? Okay, so that gives you the conclusion of the part on data abstraction, objects versus abstract data type, and declarative versus non-declarative. So you actually have 4 kinds. And if you look at the languages you use, they will be using bits and pieces of all of these. Even the stateful abstract data type is a little bit used. If you have static attributes in classes in Java, is an example of a stateful abstract data type, okay? Using static scope and higher order, we can build it, but we need cells, of course, for the non-declarative ones. But if you want to define your own abstract data type, you need this unforgeable key thing. Okay, you need a way of doing security in the language. Okay, so most languages, they don't give you this. This is kind of a new thing. Usually the languages, they hide it. Languages are afraid of them giving power to programmers. They will let you build the abstractions, but the mechanisms are kind of hidden inside, and only the compiler knows it, okay? But in this course, I'm actually showing you what's inside there. So this will help you hopefully understand better the languages that you use. Okay, so let me do a break now, and after the break, we start looking at multi-agent programming. So this is like the 1 hour concentrated presentation of data abstractions. But after that, we'll look at multi-agent. Okay. So on va faire un peu. So I'm going to talk about multi-agent programming. This is actually a really good and powerful way of programming, multi-agent. And this is based on ports,
are the communication channels we saw, okay? And so what I want to talk about now is multi-agent, and this will go through several lectures, okay? I want to show you how to do really good multi-agent programming, and then I'm going to show you a real-world system called Erlang, which does multi-agent programming in a very powerful and nice way. So this is kind of under the radar compared to systems like Java, but this is used by many, many, many companies. So I'll give you some examples of this. So typically, I mean, you are all using it, I'm sure, if you're any kind of gamer. So for example, most of the infrastructure behind the scene of Call of Duty, this game is written in Erlang, for example. And there's many examples of this, because this is a very solid, robust, multi-agent system. So this is the best way to write concurrent, large-scale concurrent and distributed systems. And so today I want to start talking about multi-agent programming, okay? I'll talk about port objects, so with the port concept, message protocols, and then I'll show you some nice examples. This one, Flavius Josephus, is an example because I want to compare multi-agent and deterministic data flow. I want you to situate that, so this will actually compare them. And then I'll show how to write big programs. And the big example we're going to see is a lift. So lift or elevator control system. So many real-world control systems controlling complex real-world devices are multi-agent systems. And they sometimes are well-written, sometimes are not well-written, but I'll show you how to do a realistic multi-agent, and then we'll talk about Erlang, okay? So the first concept is, the basic concept is a port object. A port object has an internal memory. So this is a state diagram. Huh? It has an internal memory, and if you send a message to that object, so it has also a thread, then it will change state, okay? So each time you send a message, it will change state. It has an internal memory, SI, called the state. And each time you send a message to this object, it will go to a new state, and there is a function that defines how the object works, called the state transition function. So that's semantically how it works. This function will take the old state, S0, and the message, M1, and it will compute the new state. So this is like the functionality, huh? You could even, and we will see a class can be considered a kind of state transition function, huh? So we'll talk when we talk about active objects. Okay? We can define this generically. So here is a generic, this is an actual abstraction called a port object. When you call new port object, you give it the initial state and the state transition function f, and it returns a running port object, okay, with that initial state and that transition function. So it has three things. It has a recursive function, it has a thread, and it has a port. So combining a thread, a port, and a recursive function, okay? So what you do is you create a port. Remember the port has the name where you can send message, but it has a stream, which is a list that is growing. And this stream is going to be the list of messages that you send to the port, okay? And then you have a recursive function, which I call loop here, which each time a message arrives. So this case statement is actually synchronizing. So this is concurrent, huh? This will wait using dataflow until a message arrives, M, and when the message arrives, it applies the state transition function, F, state M, and then it calls recursively
then waiting for the next message, okay? So this, internally, there's a single thread. So it is a single threaded entity, a port object, that accepts messages from outside, okay? So it's combining a thread, a port, and a recursive function, okay? Now, I want to first look at this a little bit more closely, and then we'll start programming. So the whole multi-agent systems are built on top of this concept, okay? All of them, airline, everywhere, anyone doing multi-agent system will be using this concept. It's always combining a port, a thread, and a recursive function. Keep going. Okay, so let's first study this, because in this course I really want to study fundamentally. So this is the loop function, huh? So this loop function here, this is an interesting function. So this function is actually doing the state transitions, huh? S0, F S0, M1 gives F1, and so on. And each time you send a message, we'll create a new state. So that's what the loop is doing, huh? It starts with state, and it does F state M, and it keeps going when the M's arrive, huh? So, we've actually seen this function before. It starts from initial state. It successfully applies F to the previous state and a message, which comes from a list, to compute the next state. This function F is a binary operation. We've actually seen this function before, and I've told you that this is a very important function, okay? Well, this is one example where it's used, this very important function. It's also used in big data. It's one of the fundamental higher order functions. Does it ring a bell? What function that we saw before? I mean, the names of the identifiers are completely different, but it's doing exactly something we've seen before. Do you have any? Do you remember? Fold. Yes, exactly. This is a fold. This is a fold operation. Fold is a very important higher order function. It's one of the most important ones. It's also called reduce. Reduce is a synonym. This is a fold operation. That means the port objects is actually using fold. So here is fold. This is the definition of fold. So the fold, it takes a list, A0 up to AN minus 1, and an operation F, and it basically does the F's on all of them, but successively, yeah? It starts with U, some identity. This is like the initial state, yeah? A0 is like the message, and F is binary operation. So this is like one state transition. And A1 would be the second message, okay? A2 is the third message, and so on. So the fold operation is what a port object is doing, okay? It is successfully transforming a state. So this is the definition of fold. I call it fold L because this one is left associative. There's also a less efficient one called fold R, right associative, but the most common one is this one, the left associative one. So we don't actually have to define loop. So in our port object, we have this loop function. Okay? We create a port with the name P and the stream S, and we can, instead of calling loop, we call fold. So init is the initial state, F is the state transition, and S, the list, is the stream. So this fold operation is a concurrent stream transformer, okay? Okay, there's actually a small bug here. What am I doing wrong here? So I replace loop by fold, but I'm making a small mistake here. Do you see what the small mistake is? So fold is a function, huh? Functions return values. So I'm doing some small wrong thing here. Loop is a procedure. Actually, doing it right will actually show me something. So the fold is a function. So I basically have to, it returns a value eventually. Yeah? But maybe it never ends. If the stream never ends, then this fold function will never terminate. It will just keep running forever. Okay? But you can see that the new port object becomes very simple if we use fold. There's three things. It's a thread, a port, and fold. Those three things combined together make a port object. This is a fundamental abstraction, actually. This is a fundamental thing. You will see it everywhere, all over the place. A port with fold, and all of it is running in its own thread. Okay? But fold is a function. So what is the result of this function here? This out value, what is that? Well, the fold will only terminate when this list ends in nil. How can it end in nil here? Well, it ends in nil when the port object terminates. That would be termination of the port object. So if I have a close, so new port doesn't let me do that, but if I can close the port, then the stream will end in nil. That would close it. You cannot extend it, and then the fold would terminate. So doing it like this is actually very nice because it shows us out would be the final state. The final state of the stream object, the port object, when it terminates. Okay? But usually, in the examples I'm going to show you, it's not going to terminate, really, but it could terminate, okay? When you build port objects, sometimes you have to terminate them. But usually they are part of long-lived systems where they don't actually terminate, okay? So you see, this is a very important abstraction. You notice how we're combining three very different concepts together, okay? Now, we saw this a little bit already in the previous course. We saw it, but I'm not going to refresh everything. We saw examples of message protocols. We made port objects, but I didn't explain really that it was fold. Now in this course we're going a little bit farther, but I showed how to do message protocols. So a message protocol is a very important concept. If I have two port objects or agents sending messages, they will send messages between each other. And the messages, you can organize them as message protocol. So a message protocol is a sequence of messages between two or more parties that you can understand at a high level of abstraction. It actually means something. It's not just the messages, it's doing some bigger thing. Like TCP, for example. You have messages going between the nodes, the computing nodes, but at a high level, it's a reliable byte stream that is being transferred between the two nodes. Okay, so that's a message protocol. And using port objects, we can implement message protocols. And when we do multi-agent, we're going to do, of course, lots of message protocols. This is in the previous course, so I'm not going to really refresh all the protocols we saw before. I just want to refresh a little bit your memory. So simple protocols, RMI is just two messages. So you have two port objects here, client and server. You send a message to the server and it replies. Okay? We did that. We also did asynchronous RMI. So that's interesting. You send a message, but you don't wait for the reply. You immediately send a second message. And the two messages will arrive at the server, and they will each do the work in order and send a reply. So the two replies will come back in order. So this is assuming that you have a FIFO, first in, first out, connection. That's the assumption that we're going to make. We're going to assume, in many cases, that the connections are FIFO. Notice that this is faster. These two calls are overlapping. Okay? Here the two calls are separate, but they are allowed, if you allow asynchronous calls, they can overlap. And it does not change the semantics, because the server will still see them in order. Okay? And you have more of them. So here's an RMI with callback. You send a message to the server, but the server needs to get some data from the client in order to do its result. That means it has to send a message back. But this is strange because the client is single-threaded. So while it's sending the message, it's waiting for the result. That means you need to create a second thread, actually. So here, typically, the idea is that you create a second thread for doing that. Or you can use another technique, which we call the continuation. This is actually harder to program. So using simple threads is by far the easiest way. That's one idea in this course. People tend to be afraid of threads, especially Java programmers, because threads are expensive and nasty if you have states. But if you use them wisely for only declarative things, like here, they are very easy to use. So we're going to use, very often we're going to use threads, okay? And then we showed also a complicated one, asynchronous RMI with callback. So I have both the asynchronous one and the callback. So you have to create multiple threads on the server and on the client to make it work. But if you do that, it's very easy. The code is actually, this looks complicated, but the code is actually very simple, okay? So if you have any doubt on that, you should look at that, okay? But I'm not going to refresh that. I want to really go on to multi-agent systems today. Okay, and in order to do that, I want to introduce active objects because we're going to define our multi-agent systems. Very often, we're going to define them using classes. The state transition function, it's actually, you can represent it as a class. And an active object is a kind of port object defined by a class. Okay? So here we have port objects. So this is the one I just showed you. We have the state transition function and the fold. But here you have objects like we just saw in the first hour, which are defined by classes like in Java. But actually you can combine both of those, and this gives you active objects. It's a port object whose behavior is defined by a class. So it's not a standard Java object, it's a port object, it's a concurrent thing, but the state transition function is actually defined by a class. That's actually very nice to do that, because classes have very interesting properties. Okay, so I'm not going to go into all the detail, but you saw that already. You can have polymorphism using object-oriented programming. Remember? You know what that is? You can have inheritance. And if you combine these two, you can have it all for active objects. So you have these very nice concurrent port objects with polymorphism and inheritance. So active objects are actually a very nice way of doing multi-agent programming, okay? So I give you a very quick refresher on that. And then we will show an example, which is Flavius Josephus, okay? So this is the class syntax in Oz, which we saw before. This is just the syntax, okay? Kind of weird syntax, because I know the guy who did it, and he's not always happy. But this was actually the PhD of a guy named Martin Hens, who is now a professor at the National University of Singapore. Interesting, huh? So he defined this, but it's actually a very simple kind of syntax. You have attributes and methods. So these attributes correspond to cells, and the methods are procedures, semantically, okay? So here you have a class, a counter object, so initialization the counter. So these attributes are used like cells. The increment here, you will get I gets the value of I plus x. And here you can bind x to the value of I. And then you can call new counter with an initialize method. And then you can use this. So this is a standard kind of object. This object is very similar to a Java object. It behaves almost in the same way, okay? But now we're going to make this concurrent. We're going to make this a port object, and we're going to combine classes and port objects. So how do we do that? Well, we define a new abstraction. We take the new port object, and instead of having a state transition function, we actually give it a class as argument, and an init method. And it creates a new object internally, new class init, and it has its own thread, again, just like before. It has a port, just like before, but instead of the fold, we are going to use a for loop, because the class has threads, okay? So you don't actually need to use a functional operation. You can just call the object in its own thread. So this for loop is going to synchronize, like the case, on messages appearing on the stream. Okay? And you return a one argument procedure. So this looks like an object. So this whole thing, it returns an object, something that looks like an object, but it's actually running in its own thread. And that's called an active object. Okay? So an active object is like a regular Java object, except it's running in its own thread, which is not the case for regular Java objects. Huh? So regular Java objects are usually called passive objects. And the one I just showed you, which is running in its own thread, is called an active object. So you can make a distinction between passive and active objects. So all the objects you use in a Java or Python program, regular, if you use them, they're all passive objects. Because they don't have threads. They have no threads inside. When you call a passive object, it doesn't have its own thread. It executes in the thread of the caller. So if I call a passive object, I'm in a thread, and that's the thread running it. Okay? They don't have their own thread. But active objects have their own thread, and that's really important. This makes them very, very powerful and good. So an active object in a concurrent system is actually much, much easier and better than a passive object. Passive objects are, okay, so they're simple. They're what you see in Java, but they're actually not very nice. They're actually kind of broken, okay? If you want to really look at it in a fundamental way, passive objects are not nice things, okay? And here's how you can compare them, okay? So here is two threads running a passive object. So this counter is a passive object, okay? Now, when I call the passive object, you cannot call it safely from more than one thread. In Java, you learn that. If you have an object, and you call it from more than one thread, you have to protect it. You have to use synchronized objects. But if you just call it like this is one, you're calling the counter from T1, you're calling it from T2, two threads. Well, if you call them at the same time, the execution is overlapping. Oof. So that's very nasty. So you can have race conditions, and you've seen that, right? It's very bad, huh? And you have to do all kinds of weird stuff to make it work, which we will see in this course. You have to use locks and monitors and stuff, huh? Synchronized objects. So passive objects cannot be safely called from more than one thread. The method executions here will overlap. So depending on what the scheduler does, this gives you bugs. But active objects don't have that problem. Active objects are completely safe when called from more than one thread. So they're really nice to use, okay? Because an active object has its own thread. So when I call the two methods, they will execute serially in its own thread. There will be no overlap. So it's no problem, okay? And if you want it, so here's it more concretely. I create a counter object, so this one is passive. I call it in 2 threads. I increment 1, increment 1, and then I display, get x, I display the value. And now I do the same code, but instead of new, I write new active. All the rest is exactly the same. So this counter is an active object, whereas the one on the left is passive object. So it's very simple. The code on the left is buggy, and the code on the right is correct. Okay? It's very simple. Active objects, no problem. Concurrency. So this one is buggy. You understand why, right? You have seen this, huh? You understand why, but I will refresh your memory. The counter is incrementing. And the increment will read the old value of the count. So here's the instruction. Add 1 and then assign it. But these are 2 operations. So the scheduler might put the thread to sleep in between. Okay, so I read both. And they put to sleep, and then I wake them up, and they're incremented. But so that means I'm only incrementing once. This could display 1, which is a bug. It's a race condition. Huh? It should display 2 always. But the right one will always display 2. This is correct, because the 2 methods will be executed serially, sequentially, by the thread of the active object. So you can see active objects are the right way to do objects in a concurrent system. Okay? See, that's the lesson, huh? So if you want to use object concurrent system, if you use passive object, it's a mess. Okay? And if you really want to do this right, you have to do, in Java, you have to do something called synchronized object, which is technically known as a monitor, which we will see later, which is actually quite complicated, and it's kind of a mess, and I don't like it, but I will teach it to you, but you should avoid it. You should not use passive objects in a concurrent system, okay? Because it's a mess. You should always use active objects. Okay, so that's the refresher on active objects. Now I want to compare port object or active objects with deterministic data flow. So let me say here, I want to compare active objects, multi-agent programming. I want you to get a good idea how it compares with what we saw before, the declarative, deterministic data flow. I will show you how to solve the same problem, and we will write an active object program for it, and we will write a deterministic data flow program. And you see, the programs are very different, even though they're doing exactly the same thing. And the example is a very neat problem called the Flavius Josephus problem. This is a very famous problem, actually, with a lot of history behind it. And you can look it up. It's really a neat, very neat story. So this guy, Flavius Josephus, this was 2,000 years ago, almost, was a Roman historian, but he was actually Jewish. He was from the Palestine region, okay? And there was wars in those days. Rome was expanding, so they were taking over. So poor Flavius Josephus was on the side of the losers, okay? So he was in a cave with fellow soldiers, and there was Romans outside. So they were very honorable, very good warriors. So they knew they were losing. So there was 40 of them, and they decided to commit suicide, these 40 guys. And they stood in a ring in a very neat protocol, and they will count every third man, 1, 2, 3, and then the guy commits suicide. And you keep going until there's only one left. So that's a famous story. That's in part of Flavius Josephus's memoirs, which you can find in Latin. You can find translation. Flavius Josephus was a very smart guy. He managed to place himself in the position of the last guy. Where is that? I mean, each time someone falls out, it's not clear where it was. So maybe he stood in a corner, he put pebbles, he figured out he had to stand in a particular place so that he would survive. And he was the only guy surviving, so he didn't want to commit suicide. So he came out, and then he became a historian. So he turned Roman, and he made a very nice career and everything. So the guy seems to be very smart. And you can see this story. So for us, we're going to use this anecdote to write the program, to figure out which guy is the last survivor. Okay? So here's a ring of 40 agents. 1 to 40. And the way you do it is you count to 3. 1, 2, 3, and then this guy disappears. 1, 2, 3, disappears. And you keep going, circling around until there's only one guy left. The question is, what is the number of that guy? What is the number of the last survivor? Not so easy, huh? So Josephus did that for 40, but we're going to write a program that does it for any number, okay? And we're going to use a protocol for that. So we're going to define a message protocol. So these are all going to be active objects. Okay? But we will also do it using deterministic data flow. So they will be stream agents reading streams. So we will write 2 programs. One of them will do this using active objects, and the other program will do it using these streams where you have input stream, output stream, purely deterministic declarative. So you can compare the two. You really need to compare the two, okay? So I first define the protocol. Let's say, okay, so I create a message called kill XS with 2 arguments. X counts how many live objects you traverse. 1, 2, 3, 4, 5, 6. And S is how many live objects are left. So you start by sending kill 1n to the first object. Kill 1n here. And then you count. So the first object, it's not a multiple of 3, so it doesn't commit suicide. So he sends kill 2n to the second one. And then this one sends kill 3n. And the third one sees 3 is a multiple of 3, so he disappears. And then so the n becomes n minus 1. You see, there's a protocol. Huh? So when an object receives kill xs, if it's alive, and s is equal to 1, that means there's only one live guy left, then it is the last survivor, and then we're done. Okay? And that is the surviving object. If it is alive, and x mod k is 0, then it's a multiple of k. The k would be 3, but we're going to make a general program. So if it's x mod k is 0, then it becomes dead, and it sends kill x plus 1, s minus 1 to the next object. You see, x counts the number of live objects, and s is how many live objects are left. So if it kills itself, the s becomes s minus 1. Okay? If it is alive, and x mod k is different from 0, then it stays alive, but it increments x and sends kill x plus 1s to the next object. You see how it's going on? And if it's dead, so the dead objects in the ring is like a ring will stays there. If it's dead, it just forwards kill xs, doesn't do anything else. Okay? So it has a state, alive or dead. So that's the protocol. And now we're going to implement that. Okay? So let me show you some code now. So here is the code, but maybe I actually copy it to the mother because it will indent it and it'll look nicer. So I have to start this one again. eventually we start. The Docker image is so huge it takes some time, so I put it here, edit, paste. Okay, so here is the victim class. So each object in the ring is this class, and it has some identifiers. It has its identity, the number. It has the alive state, which is true or false. It has the step, which is the k, how many men. And then there's a variable last, which is the last survivor, okay? And also, because it's a ring, each object has to know its successor. So successor, SUCC, will actually tell me what is the next object in the ring, so I can send a message to the next object. And then the protocol is defined using this kill method. Okay, so each message corresponds to a method here. You see how it works, huh? So kill XS. If I'm alive, then I do this. Else, I send kill XS to the successor. You see how it works? If I'm alive, and S is equal to 1, then I'm the last one. I'm the last one, and last this is going to be a variable that is bound to the last survivor. So I will bind last to my name, the number of me, okay? So this will tell me the number. Else, if X mod step is 0, then alive is false, I've become dead, and I send kill X plus 1, S minus 1 to the next object. And if it's different from 0, I send X plus 1, S. So I only kill myself if X mod step is 0, okay? Otherwise I don't. You see how it works? So that's how the protocol works, okay? So I can define that. But there's also, that's the definition, but there's a program now that uses this. So here is the program. Command C. Let me put it here. So I'll show you the program now. And that's it. It's the victim class. So it's not so complicated. So I define a function called Josephus with n and k. So I'm going to call it with 40 and 3. And I will use Oz arrays. I will make an array of n active objects. Okay, so this is an array from 1 to n. So I'm not going to explain how arrays. So a.I will be the ith element of the array. It's like a vector. And this is a new active object of class victim, which I defined above. And it has the name I, so each one is numbered. The step is k, and there's a single variable last. So all of the objects will know the variable last, and it's only the last survivor that's going to bind it. Now I connect them into a ring. So I do for loop from 1 to n minus 1, and a.I, the successor, is a.I plus 1, right? Except at the end, a.n, the successor is a.1. You see, it's not so complicated, huh? And then, to start the whole process, I send a first kill message, 1n to a.1. And that's it. So it's not so complicated, huh? So this is a very nice concurrent program. Each of these active objects is going to be its own thread. Okay. So let me run this. Define the feed region. I forgot to do a declare, just a sec. Oh no, I have to define new active, I'm sorry. So I have to define this abstraction first. Let me define it. Okay. Otherwise it's not going to work. This is an abstraction. Let me define this. Feed region. Okay, good. Now I have Josephus. Let me define this one. Like this. That. Okay. Okay, good. And now we can run it. Let me do a simple one first. 5, 2. Okay. 3. Is that correct? We can check it, huh? So we had 5, 2 is a simple one. We can do it by hand. 1, 2, 3, 4, 5. Start here, and you start every 2. So I get rid of this one, 1, 2. I get rid of this one, 1, 2. Get rid of this one, 1, 2. So the one left over is 3. So that's right, huh? Seems to be working right. But now let's do what Josephus did. 43. And now we will relive the exciting moments that Josephus was in that cave. Imagine that you're in the cave and you're figuring it out. You want to survive, okay? You don't want to kill yourself. So this is very important for you, okay? Imagine that. You could make a movie on this, huh? Right? Okay. 28. That's it. He has to put, but he repeats it again. He makes sure he doesn't make a mistake, huh? And while they're actually counting it, he is very careful to make sure that they don't make a mistake while they're counting, huh? Of course, at 1, 2, 3. This guy, okay? Not someone else. So he's very, very careful because it's his life is at stake. 28. So he puts himself in position 28. He survives, and the rest is history. And now we can read his memoirs and relive these exciting moments. Okay? Okay, so we're almost at the end for today now, but I still haven't shown you the deterministic data flow program. So here you see the program using active objects. So it's very reasonable, huh? It's very nice, right? It's easy to understand. It's completely concurrent. And we don't care. You can send messages to active objects and it will be correct. There's no race condition problem. And each message in the protocol is just a method. Okay? So this is the protocol. And then you have another piece of code, which is we're setting up the ring. We create an object, we set up the ring, and we start it. So it's actually very simple, huh? Right? It's quite simple, huh? And you could program this in many languages, like Erlang or so on, huh? And it works very well, right? And you can even do more. Let's say you have 1,000 in a ring. Thousand guys in a ring, and you count every 10th guy. 63 is the one that survives. So it works for any case. So it does much better than poor Josephus. He had to do it all by hand. Huh? So that's interesting. You see that, right? Okay, so I still haven't shown you the deterministic data flow one, but you'll see how different it is. It's very different, actually. But it will do exactly the same thing. And you'll see also, it's much shorter. The deterministic data flow will only be half the lines of code. How is that possible? This seems to be pretty short, right? I mean, this is not complicated, no? It's exactly the protocol. We're just writing down the protocol. That's it. We're not doing anything else, really, huh? But the deterministic data flow one will be even shorter than this. But it'll be doing exactly the same thing. Okay, so we'll leave that for next week. Next week we will see the next chapter in the exciting story of Flavius Josephus. Question?
Could I request that you check the slides that are on Moodle, because the section on...
There's a mistake, or...
No, there's missing slides.
There's missing slides, yes. I updated the slides to add the active object slides. Yeah, I will update the slides on Moodle. Yeah. I do that today. To get the most recent version. Okay. Very good.